Okay, so what this chapter gets at now, last chapter was just learning all of the rules for derivatives for any functions. This is now the applications of the derivatives. What do we use derivatives for? What can they be used to find? So the first thing that we start off with is at the top here. Whenever you see extreme values, that's just referring to maximums and minimums. So we've already dealt a little bit with maxes and mins in your life. We're certainly going to add some layers to that, but it's still the idea of what's the highest point, what's the lowest point. First thing, we want to differentiate between a couple different types of maximums and minimums. So we have what we would call local or relative. Those are just high points on our graph that locally are high points, but they're not necessarily the highest point. All right, so those we either use relative or local. Those words are interchangeable. They're both used kind of the same amount. Versus the absolute or the global max or min. Absolute kind of is the nicest way to write it. It is the absolute largest value on our graph, okay? Or we can also use global. So an absolute max then would always be a local max, but the converse of that would not necessarily be true. So to kind of get into that idea, just make sure we understand what that's getting at. I want you to label all the maximals and minimals on the graph below, and we're just going to draw something in. So put a dot like right here, and then I won't be, without having thought about this too much, other than one little thing, just sketch in a graph that kind of looks like this. And then we're just going to go around labeling our maximums and minimums, our high points and our low points, and using the correct prefix in terms of if it's a local or relative, or an absolute or a global. So as we start working our way left to right, the first one we're going to talk about is this one right here. This is a high point on our graph. So this, we would say this is a max, but then the question is this the absolute max? So if we look at overall that graph, we would see that's not necessarily the highest point overall. So we would just call this either one of these words, whichever you prefer, local or relative. I'll use local in this case. We would call that a local max. So in that general area, it's a high point, but it's not the highest point. If we continue on, we would eventually get to this point right here. This is a minimum. If we compare that to every other spot on the graph, we can see that that's the absolute lowest point on our graph. So we would either say that's the global or the absolute minimum, whichever you prefer. As we continue along, you'll see a high point here. So this is a max. That again is just locally a max. I used local last time, so I'll use relative this time, since they mean the same exact thing. We get a 4th spot right here. This is a local min. And then finally, we get to the end of the graph here. And finally, this is not just our regular max, this is our absolute max. It's the absolute highest point on our graph. Okay. What I'm then going to have you do, since we have like 5 of those, label those. This is 1, 2, 3, 4, and then 5. What I could have had you do, or what I could make you do now, sometimes if we're in the building, we do, I just have you draw any graph you want. And no matter what kind of a graph you draw, if you were to go around your graph labeling your maxes and mins like we just did, one of these 3 things is guaranteed to be true at every point that we just labeled. All right, and those 3 things are: the first derivative would equal a 0. So if we look at the 5 that I just labeled, there should be a few of them where our first derivative, which is just the slope of the graph, is equal to a 0. So the reason I had you label those is so we can now identify which ones are those. So if you look at number 1 and number 2, we have nice slopes of 0 there, and we not coincidentally have a max or a min there. Another thing that could cause a derivative or a graph to have a high point or a low point is number 2 here, that the derivative would not exist. So if you look at number 4, there's a sharp corner there. So many times a sharp corner could result in you having a high point or a low point on our graph. So we would put number 4 in that spot. And then the third and final place where we can get a max or a min, we call it an endpoint. So if we look at number 1 and number 5 on our graph, those are what we consider endpoint. It's our starting value and our ending value. Those are always going to be some sort of a high point or a low point. So no matter what I were to draw in, if I were to create a different graph over here, and like this is a max and that's a max, well, here my slope is 0, this is an endpoint. Here my slope is 0, this is an endpoint. One of these three things would be true for any graph you would ever look at in your entire life where there's a maximum or a minimum. One of these three things would be occurring there. Okay, it's the only three things that could occur to make our graph have a high point. So that big deal today. We'll talk about that a lot. Next thing, critical point. So when we start talking a critical point, basically just means something interesting is going to be happening there. Critical points, when you see that, are when our first derivative is either 0 or your first derivative does not exist. So if I ever say find the critical points, I'm basically telling you to find where the derivative is 0 or find where the derivative is undefined. All right, those are our critical points. Many, many times, those are going to be maximums or minimums. But you can see here, just because it's a critical point doesn't guarantee a max or a min, but a lot of times it is. So that's why we're going to use those. Because really all that is number 1 and 2 above, right? These are our critical points. And then along with our endpoints, that's where we can get maxes and mins. All right, next thing, you have a little theorem from your geometry days. So it's called the extreme value theorem. So extreme values indicate maxes and mins. So this applies to the idea of high points and low points on our graph. There's 2 conditions for this. So in order for the extreme value theorem to be applied, we need a continuous graph on a closed interval. And as long as it's a continuous graph on a closed interval, then our function must have both a maximum and a minimum. There's no way it could not. So the way we're going to kind of show that is go ahead and draw a cheap little XY plane there. And I'm going to put A here, we'll put B here, and I'm going to start A down here, and I'm going to finish with B down here. So that's going to be our closed interval that I'm going to talk about. And as long as I start at A and go to B and remain continuous, so you guys just copy mine the first time, so let's just do this. Notice how my graph is continuous. It has a defined starting point and a defined ending point. Okay, so it's on a closed interval. The extreme value theorem is saying since we satisfy these 2 things, continuous on a closed interval, we have to have a high point and a low point, and we pretty clearly do. We have a maximum here, we have a maximum there. Here's a minimum, here's a minimum. Okay. If you go to B, do the same thing. Oops, that's going to be B. This is A. And then now connect those 2 points however you want. So now we can have 32 different graphs here. Just make sure it's a continuous function. Then, no matter how you just graphed it, if I were to look at everybody's graph right now, since it's a closed interval, we started at A, we finish at B, and as long as your graph is continuous, every single one of you should look at your graph and see that there's a clear maximum on that graph and a clear low point on that graph. Okay? If not, you've discovered something very powerful. All right? So now, in part C, usually in a room, in this case, a screen on my TV, of smart people, there's usually a few people that think, you know what, I can show this is not always going to be true. So try to now draw something in letter C that is a continuous graph that starts at A and ends at B that you would think would not have to have a maximum and a minimum. All right, anybody got that? What we typically always draw? Yeah, Thomas, what do you got, Thomas?
Horizontal line.
Yeah, so most people probably come up with that a little bit. So let's say I draw a horizontal line that starts at A, goes through B. We'll say mine goes through 2. That's a continuous graph. It's on a closed interval. So according to this extreme value theorem, that should have a high point and a low point on it. All right. So the way we can now approach this is if I now ask you this question, so this actually you do a little bit in math 1 and math 2. The absolute maximum y value could you look at that graph and give me the largest y value that that graph would ever hit? Does it have a largest y value? Yeah, right? When we say 2 is the largest y value that we have. So that satisfies this part of it, right? We do have a maximum. And then it's a bit of a cop-out, but nonetheless, we go with it. If I ask you what is the absolute smallest y value that that graph would ever hit, doesn't it at the same time have the smallest y value? All right, so we also get a 2 right there. All right, so it's one and the same. All right, it's like when Kevin's in class yesterday, he's not only the tallest student in my class yesterday, he's also the shortest student in my class yesterday. All right, so we can qualify as both. Okay, so that's the extreme value theorem. As long as we're continuous on a closed interval, all right, we have a max and we have a min. All right, now to kind of show that further, we're going to fill out this little table here. Understand what this graph looks like. That graph by itself is a continuous graph. It's just a parabola with a vertex at 0 that opens upwards. So all of these are going to be continuous. So the same exact graph. There's no issue with this graph. But what does change is if I look at my domain, the one that I drew, we go from a negative infinity to infinity. So we have a continuous graph. This is not on a closed interval, however, at least not the first row. So what we're then going to come over here and do, if I ask you to fill in these two things, what's our absolute minimum y value, and then what's our absolute maximum y value? If I ask you for the absolute minimum, we can look at our graph over there, since it's defined everywhere, and it's pretty easy to see the smallest y value that that graph ever hits would be a 0. If I ask you what the largest y value is, the fact that that thing continues to increase forever and ever and ever means we don't have one. There isn't any. And that's okay. It doesn't contradict the extreme value theorem, because while this is continuous, the negative infinity to infinity is not in a closed interval. Okay. Now, when we go to the next one, so let me try to squeeze this in. Let me just erase this. It's messy. So if I go to the next row, I'm just going to extend this row with this graph. It's still the same graph, but now I only want to go from 0 to 2. So now I'm going to start at 0. We're just going to come over here, and then I'm going to stop at 2. So now this one is continuous still. X squared by itself is continuous. It is on a closed interval. So when we go to answer this question, this does satisfy both conditions of the extreme value theorem. That means we better get one of each. We have to. If we look at that graph just visually, we can tell that there is a high point and a low point. So we already know that they're existing. The absolute lowest y value, don't need to rewrite that, is still the y value of 0. We're right at the origin. The absolute maximum value, and this is always y values, so that's something to be aware of. So yeah, it's occurring over here at 2. That's the x coordinate. What we really want to know is what's this y coordinate. And in this parabola, when x is 2, we should get a y value of 4. Notice how we have both because we satisfied both conditions. All right, next one. I sketch this guy in. So now we have x squared again. But notice how the 0 is open. So now we have a hole in our graph at 0, and then we increase just like we did in the one above it until we hit the x value of 2. So while this is a continuous graph, we are not on a closed interval. So we might get a max, we might get both of them, we may not get any. It's not guaranteed. So if I now ask you the absolute min and the absolute max, it's the absolute max that's probably the easier one now. Definitely still that y equals 4. The absolute minimum, though, now that there's a hole in our graph, we just get closer and closer, and this poor guy just tries to get closer and closer and closer to the y value of 0 for the rest of his life, but he doesn't ever get there. So the fact that there's a hole in our graph means we do not have a minimum at all at that point. We just get closer and closer and closer to 0 without ever actually getting there. All right. All right, and then the last one. They're both now open. So an open dot here, open dot there. That's what this is telling us. So now what we just talked about applies to both spots. So we still do not have a minimum because the same exact thing in the previous row is happening in this row. But we also have an open dot at the highest point on our graph. So we get closer and closer to a y value of 4 without ever getting there. It just becomes basically 3.999999 forever and ever and ever. So because of that, we don't have a max, nor do we have a min. Okay? So that's kind of the extreme value theorem. The only one that satisfied that condition was this row here. And that's why you ended up with both of them. We had to. All right. All right, now on the next page, let's go to the next page. I'm going to skip one. Actually, I'm going to start with 3 because I think it's the easiest to understand. What I want you to do, I want you to find the critical points. So if you remember, the critical points are when your derivative is either 0 or undefined. And then you're going to state the absolute maximum and minimum values of the graph, just like we did on the front page. Okay, except we won't necessarily know what all these look like. The reason I like starting with 3 is because we know what this looks like. And then we can do the work and then compare it to our graph. All right, so first and foremost, they want you to find the critical points, or I do anyway. And the critical points are when your first derivative, so we're going to take our derivative. We'll find the derivatives are much easier in this chapter. And we want to know, when does the derivative equal 0, or when is the derivative undefined? So one of the things we're going to do is basically right off the bat, at this step here, look at your derivative and think about, is there any x value that would make that undefined? And what I mean by that is, let's say our derivative was 1 over x. Hopefully we would all agree then that x cannot be 0, so that makes our derivative undefined. Well, if you look at our derivative currently, our derivative is just a 3x squared. There's really no limitations on what we could plug in right here. So there really is no place where our derivative is undefined. So we don't have to worry about that. We can also set that equal to 0. That's what we do for critical points, where the derivative is undefined and when our derivative is equal to 0. Set that equal to 0 and then solve. So divide both sides by 3. Take the square root of both sides. And our derivative has a value of 0 at x equals 0. Now, what we then do with that, and this is how you want to write it, and it's very appropriate considering we have an election pretty soon, but you actually want to identify what we call candidates. So you're going to write that out. The places where we can get maxes and min, there's only 3 places on the front page we said we can get maxes or mins. When our derivative is undefined, which this derivative doesn't have anywhere where it's undefined, so we didn't get any candidates from that. Also, when our derivative is 0, we did get a candidate from that, so we're going to list that as a potential answer or potential place where we get one. And then the third place is at your endpoints. We definitely have endpoints. There are these -2 and +1. So x equals a -2 and x equals a +1 are our candidates. Those are the only 3 places any graph could have a high point or a low point. And since these are our 3 candidates, the answer has to occur at one of those 3 places. So what we then just do is figure out what is the functional value at those 3 x coordinates. Whichever one has the largest value must be the max. Whichever has the smallest value must be the min. So if I take 0, we're just plugging it into the function value now. 0 cubed is going to give you a 0. Take your -2 and cube it, we get a -8. Take your 1 and cube it, we're going to get a 1. Those are the only 3 possibilities for our answer. Since those are the only 3, if I now ask you what is the absolute lowest or smallest value that that graph could ever hit, if we just look at these 3 guys, this is the smallest of our 3 candidates. So it has to be the y value of -8. If I ask you what's the absolute largest y value that this graph would ever hit, of our candidates, 1 is the biggest. So 1 would have to be our answer. And then that's how we present the answer and write that. If you think graphically, and that's why I like doing this one first, the x cubed graph from a -2 to -1 would look like this. And we'll stop it here at 1. So isn't this the smallest y value happening at the -2? And then our largest y value is happening at the 1. It's continuous the whole way on a closed interval. That's why we're guaranteed to get both of those. All right. All right, so number 4, same exact process. What we want to identify is what are our candidates. And the way we get our candidates are from the 3 places where we can get maxes and mins, where the derivative is 0, where the derivative is undefined, and at our endpoints, from what we did on the front page. So right away, as soon as you see these guys, it tells you have endpoints. So we're going to list those as candidates. And then now we've taken care of this guy. So I'm going to cross that out. We've already addressed the fact that we have endpoints. The other 2, so 1 here and 2 here, involve our derivative. So we want to take our derivative, and that would give us a 1/3 x to the negative 2/3. We want to do 2 things. We want to set it equal to 0, all right, because that's this part of it here. And then as you set that equal to 0, let's simplify it. So I'll still have my 1/3, so the 1/3. And then that x has a negative exponent, so we're going to put it into the denominator. And then if it's a 2/3 power, it should be a cubed root of x squared. So actually, let's talk about this first, the derivative being undefined. Can we now agree, since I have an x in my denominator, that if x is 0, I would ultimately be dividing by a 0, and it would make that undefined? Yeah. So x equals 0 makes our derivative undefined. That's included in our candidates. The third and final now is solving this equation, because whatever this solves for would give us another candidate. So if I go through and solve this, I'd multiply both sides by the cube root of x squared. These would cancel. I'd have to multiply the other side by the same exact thing. But since we're multiplying by a 0, I would just get 0 on the left. And then on the right, I just get a 1/3. So in an attempt to solve for that x value, what we got is something that's not true. So what that basically means is there's no place where our derivative was 0 here. If we were to graph it, there's no nice horizontal tangent. So these are our only 3 candidates. All right. So these are the 3 then that we now just say, what's f of -1? What's f of 8? What's f of 0? The largest of that you would say is our absolute max. And then the smallest value that we get from those 3 would have to be our absolute min. Know what this equation is. If this is x to the 1/3, don't overthink that. That's a cubed root of x. So if I take a -1, the cube root of a -1 is a -1. If we take the 8, the cube root of 8 is 2. Well, I gave it to you as an 8. And then the cube root of 0 is 0. If we look at those 3 all lined up as our only candidates, the 2 has to be the max. So we come down here and say y equals 2. The -1 is the smallest possible value we would get, so that's our absolute min. All right. Okay, I like doing those 2 first, and then I want to go up to number 2. I want to make sure we get the ones that I want you to see in our short time. So if I go up to number 2, as we go to list our candidates, there are 2 very obvious candidates because we have endpoints. So right away, our answer could be at -2 or 3. Any other candidates come from our derivative. So we'll take our derivative. And it would be where our derivative equals 0. So we'll set that equal to 0 and simplify it. So we'll get our 2/3, and then that should be a cubed root of x in our denominator. So it's either where the derivative is 0, that's why we said equal to 0, or undefined. So similar to the one that we just did, if this x is a 0, you're going to get a 0 in our denominator. It's going to make that derivative undefined. So 0 is a candidate. And then similar to the one that we just did, if we actually attempt to solve this and multiply that cube root of x over, that's going to cancel. You're going to get a 0 on the left, set equal to a 2/3. That basically means there's no solution to that equation. There's no other candidates. So from there, this is what we've been doing. Find f of -2, f of 3, f of 0, and then we pick between those the largest and the smallest. And this equation is a cubed root of x squared if we rewrote it. So if I take a -2, hopefully I can squeeze this in here, it should be the cube root of 4. F of 3 should be the cube root of 9. And then f of 0 is 0. Here are the 3 y values now that you're comparing. The smallest one is obviously the 0. So that's our absolute minimum. And then I'm pretty sure we would all know that the cube root of 9 is going to be bigger, whatever it is, than the cube root of 4. So our absolute max is the cube root of 9. All right. All right, so now real quick, go to number 5, see if we're understanding, see if we can get some candidates, see if we can kind of work through our process there. Just again, take your derivative, we know how to do that. A couple candidates should be very obvious. All right, then we should get 2 candidates for sure. All right, with absolutely no work. You have endpoints, so 0 and 5 right away. With absolutely no work, we can list those. The other 2 you're going to get from your derivative. So you're going to do 1 over the x plus a 2. And then we do 2 things. We set it equal to 0 and then try and solve that equation. And then we also look to see if there's any x value that makes this undefined. So if I now look at this here, would we all agree that -2 makes this undefined? Yeah. So now typically that's going to be a candidate. In this problem, it's not going to be a candidate. And the only reason it's not going to be a candidate is because it doesn't fit in the interval in which we're concerned about. The -2 doesn't fit between 0 and 5. But it made our derivative undefined. Normally that's one we then need to consider. All right, but we're going to ignore it because of the interval. If we try to solve that, it's the same thing that happened before, is these are going to cancel. I still get a 0 on the left when I multiply by that x plus 2 doesn't equal to 1, so there's no solution there. These are our only 2 candidates. And the fact that the natural log is a continuous function, we know what that looks like, and it's a closed interval, means we better get one of each. We better get a max, you better get a min. So all that means is one of these is the highest point, one of these is the lowest point. So then we take these, plug them in. If you plug in the 0 here, you're just going to get the natural log of 2. If you plug in the 5, you're going to get the natural log of 7. We need to know what the natural log curve looks like. It's a constantly increasing function. So whatever value we get at 2, we should be able to compare to 7 and see that 7 is the bigger of them. So the natural log of 2 must be the absolute minimum. 0 would not necessarily always be a candidate. No. And has it been one in all of these? Suppose it has, but no, it will not always be a candidate. No, good question. Just a coincidence so far. All right, and then the absolute maximum then is the natural log of 7. All right. Okay, we've got 2 minutes left. There's no way we're going to get through another one of these. Bring this tomorrow. I do want you to see number 6 and 7, so we'll probably hit those in the first 5 minutes or so before we move along. But yeah, we're not going to get that done in a minute and 10 seconds. Okay. All right, so bring this tomorrow, and again, I'll try to get the packets made and then give you that information when you can come pick those up, hopefully. Okay. All right, so with that, we'll see you guys. Have a good night. You can have an extra 2 minutes off. All right, see you tomorrow.